Hi, my name is Sergio Ardiazabal. I'm a physics programmer at Epic Games. I work in Real Engine simulation team. For the past year and a half, I've been working on a tool called the Chaos Visual Debugger. We shipped it a few months ago in Unreal 5.4 as beta. For Unreal 5.5, we continue working on it, and we bring in several new features and improvements to it. And the reason I'm mentioning this is, as you might already know by the name of this session, today we are going to be talking about debugging physics in Unreal Engine. Especially, I want to focus on show you how you can use a tool like the Chaos Visual Debugger to diagnose any physics-related issue you might be experiencing in your game. So, this is the plan for today. First, I would like to go over what is the Chaos Visual Debugger. If you work with a physics engine that has a bit of visual debugger, you know what it is. In case you don't, we will do a short description of what a visual debugger for physics is, but then we will jump right into some specific details about our visual debugger. Also with some information about the Chaos update loop, which I think standalone is a good piece of information to have. You need to dive into Chaos code, but we also need it for future sections of this presentation. With that out of the way, also the next section will be a walkthrough of the Chaos Visual Debugger user interface. Actually, I will divide this in two sections. The first section will be presentation mode like this, where I will focus on just two main sections of the user interface. And one of them will require us to dig a little bit deeper into the Chaos update loop. I will touch on things like network physics and async physics, which is something the Visual Debugger needs to support, and also same as before. I think it will be a good standalone piece of information. And then the next section of the walkthrough will be a live demo. I have Project Lyra up and running. Hopefully it stays up and running when I get at that point. Where I will try to show some end-to-end workflows, the different ways you can record the state of simulation either in editor or in a package build using the Visual Debugger. And at the same time, we'll do a walkthrough of the rest of the user interface I didn't get to. And hopefully, I didn't run out of time by then. And the plan to close the presentation is I want to talk about what are the future plans for the Visual Debugger, because as I mentioned before, we ship it as beta, and we still beta in 5.5, so we have several new features we will be working on. I want to share with you what are the future plans to it. And without further ado, let's begin. So, introducing the Chaos Visual Debugger, or CVD for short. So, what is the Chaos Visual Debugger? As I mentioned before, if you work with a physics engine that has a visual debugger, you know what it is. But to put it simply, a visual debugger for physics is like a system and tool that allows you to record the state of the entire physics simulation or your game or application within a period of time, and then usually dumping all the data into a file. And then you are able to load this file in this tool, and you have a user interface similar to a video player where you can scroll back and forth in time, see the state of the simulation at those times. But unlike a video player, you can actually go into the 3D scene, 3D visualization of the scene, and interact with the object to see more details in a details panel kind of thing, like a level editor. CVD is just like that. From Unreal 5.4 or 5.5, it's a editor tool, can be accessed within the editor. I will show you how later on. But we also work in a standalone version. I mentioned in this slide as experimental. See, if CVD overall is beta, the standalone program is experimental because Unreal 5.5 is available as source. You can compile it, but I don't recommend that yet. For 5.5, I recommend to use the editor tool version of it. Some more specific details about this. Although it's an editor tool, it does not depend on any project-specific asset data, which means you can do a CVD recording for a package build of your game and any version or any stream you're working on. And you are able to visualize that in a vanilla Unreal editor. That, for example, is important for us because it means a CVD can be a tool to allow us to provide faster support to licensees, because now if you have an issue, you should be able to do a CVD recording of the issue, share that with us, and we'll be able to quickly see the setup of your scene from the physics point of view, and either figure out what is going on and provide advice, or be able to ask more relevant questions. And the same applies internally. We work in multiple products, multiple branches across multiple teams, and having a generic way to share what is going on in the physics scene across team is very useful to save time to not having to sync to a specific branch to be able to start providing help. Another key point I want to make, CVD is able to support large worlds. In fact, the video that is looping in the background is showing city sample. The Visual Debugger is able to render almost in real time what is going on in the game client. You can see in the right. For 5.4, that is working. It's kind of rough. For 5.5, it's way better, and we will continue making faster and using less resources in future releases. Another thing I wanted to mention about the Chaos Visual Debugger is we use Unreal Trace as data transport, which is the same trace system used for Unreal Insight or profiling tool, and another tools also within the engine are starting to use it. So that not only provide us with a very strong foundation, but also provide us out of the box the groundwork for some features like CVD platform independent. You can do a CVD recording from a game console or mobile phone. You should be able to inspect it on your workstation as long as you run the editor. Everything you can choose to record, dump all the data into a file, or you can do like the video that's looping in the background, see it in real time, which eventually also is dumped to a file. Part of using Unreal Trace also allows us to provide both of those things over the network. Obviously, you have the limit of the bandwidth, but over the local area network, the LAN network should work. Something I want to dig a little bit deeper before I move on is I mentioned a few times simulation state. So I want to say specifically what I mean with simulation state, what we actually record. So we record pretty much for particle state or rigid body state. We record pretty much all the state, velocities, accelerations, mass properties, all the set of flags that define the behavior of the body, like have gravity enabled or not, the actual state, sees awake, sleeping, or a kinematic body. And this is a small screenshot of the details panel. We'll see it a little bit more in the live demo. And collision geometry, we not only record the actual collision geometry to visualize it, but also we record and offer to inspect it in the Visual Debugger, the entirety of what we call the shape data. Everything when you set, for example, your static mesh editor, you add the collision shapes, and you need to set this collision query only, query and physic, or both, or you are in the blueprint editor, or you are setting the collision preset, or creating a custom one where you set how each collision channel responds to if lock, ignore, or overlap. CVD is able to show you that information for each shape you see in the Visual Debugger, which is useful if you're trying to track down an issue where collision doesn't work as you expect, or you're doing a sync query and you didn't get a hit. You can see if the actual preset was set up correctly within the Visual Debugger. And collision constraints, the Visual Debugger records pretty much the entire state of the collision detection system. Here on the broad phase, we record the intermediate state we call mid phases, which is the part structure containing the potentially colliding particle pairs and the constraint that was generated for that. But you are debugging, for example, inspecting the narrow phase, we also have access to the entire contact manifold and some details like the push-off forces, the contact normal, and so on, a way to visualize it. Joint constraints, we support joints. We record the entirety of the joint settings and the state. You will see in the user interface the Chaos Visual Debugger something called character ground constraints. This is a constraint type used for the physics-based character movement system we are working on. So the Visual Debugger also supports it. Sync queries, a big one. We record pretty much the entirety, any sync query you do via the URL API, line traces, sweep, overlaps. We don't only record the inputs you need to create a query, like the shape, positions, when applicable, or any specific parameter, like see this trace, for example, this sweep need to trace against complex geometry or not. We also record the results, and if it was hit by the query, you are able to see it in the Visual Debugger. And also record the intermediate state. When you do a query, you will go to the acceleration structure, an IBV3 for us currently. You can, when you do that, the acceleration structure will resolve the subset of potentially matching collision geometries. And then we iterate on them and do what will be the narrow phase to verify that the query actually match that collision geometry, also verify the collision filter we might have. And CVD records each shape that was evaluated. So this is a useful feature I will try to see. I have time show you in the live demo. For example, you are doing a sync query, you are sure, let's say you do a sweep, you are sure you should be hitting an object, and visually looks like you should be hitting an object. You can use this to try to see if the shape was evaluated at all or was rejected, maybe because you have the wrong collision preset or something else. But let's say, for example, that the shape was not evaluated at all, but visually it should have been hit. So that means probably something, there is an issue in acceleration structure. It could be that this is a bug in IBV3. We have a few of those. They are surely fixed. But also could be that for some reason, the BB tree or the acceleration structure we might be using was fed invalid data. So CVD is able to record the entire state of the acceleration structure, and you can visualize in the Visual Debugger to see either you can choose to see how the tree is built, or you can just to see the bounds of each object that is inside the acceleration structure to verify if it was correct or not. And then I will touch a little bit later on. We also have support, initial support for the network physics we are working on. So when I say what kind of data record is pretty much all the data, but I had to make a distinction, at least on 5.4, 5.5. We record only pretty much all the data from the physics thread state of the simulation. So what I mean with this? In Unreal, we have two versions of the physics state of the simulation. We have the game thread state, and we have the physics thread state. The game thread state is basically the state you have immediate access for any of the game framework APIs. The physics thread state is the state where the solver logic, the physics solver logic, actually iterates on to advance the simulation. So I prepared a graph to try to give you a glimpse on how that is supposed to work. My version was very much programmer art. Shout out to the team that actually make a nice slide for this. So this is intended to represent a typical frame, game frame, in sync physics mode, which is the default mode we ship on and is widely supported. So at the top, we have the game thread. At the bottom, we have the physics thread. And in the middle, we have this object we call the Chaos Marshalling Manager, which is an object in charge to marshal the data between the two threads. Some small clarification I want to make. In this, I'm showing the physics as a single thread, but in practice, we do physics work across multiple threads. We go wide at different stages, but for the purpose of the presentation, we can think about it as a single block. So, and a typical flow inside a frame, it will like the, let me see if I can use the pointer, yeah. The frame starts, the game thread will figure out what data is dirty and needs to be updated and processed. So it will push that data to the Chaos Marshalling Manager, and then it will start a task in the physics thread to actually advance the simulation. Once it does that, the game thread needs to wait for that physics work to be completed. Otherwise, it cannot finish the frame. That is why it's sync physics. So while the game thread issues the physics task, continues to work, and eventually needs to wait to the physics work to be completed, the physics thread will pull the data from the Chaos Marshalling Manager, process it, and push back any result to the Marshalling Manager, and then complete its work and so on. This means then the game thread, if we are waiting to finish the frame, is able to continue, pull the data, and process it and move on to the next frame. So why I'm making this distinction now when trying to talk about the Visual Debugger? First, as I mentioned before, I think this might be useful if you need to dive into Chaos and you want to see how the flow works, in case you need to debug that. But also, I'm making this distinction because if there is an issue in this synchronization step, right now in 5.4 or 5.5, the Visual Debugger might show you that everything is correct when actually it's not, because the game thread state is not correct. So it can be a little deceiving. So something to keep in mind. For future versions, we will also record the game thread state of simulation and visualize that and allow you to compare between the two. But for now, it's not available, so something to keep in mind. So now, so you wonder, in case you don't, I pretend you do just to hook up to the next session, how we will represent, for example, having a game thread state, a physics thread state, the Visual Debugger. Let's go dive through the user interface. So first, I want to show you how to open the Visual Debugger, which is funny because when I wrote the user guide documentation, it's the only thing I forgot to put in the documentation. So now it's in the presentation at least. So you can just, the tool menu, debug, Chaos Visual Debugger will show you again in a bit on the live demo. This is what you will get. It has a file loaded, so it looks cooler, but it's pretty much the classic level editor layout. Viewport, a scene outliner, details panel. Detail about the details panel, in the Visual Debugger, we have multiple details panel running at the same time with multiple instances, one dedicated to rigid bodies, one to the scene queries, one to collision data, and one to the rest of generic constraints like joints. And then we have the playback controls that we will dive into a bit. For the viewport, the only thing I want to focus right now is in the show menu. As I mentioned before, CVD records a vast amount of data, different categories, but most of that data is disabled by default on the visualization. The reason is if you enable everything, it becomes a total visual noise. So by default, we disable everything except collision geometry. So if you are expecting to see a scene query and you're not seeing it, I recommend to go to the show menu, find the correct category, make sure that the enable draw flag is enabled. Each category has an enable draw that is basically the main way to enable visualization for the entire category. And then there are some sub flags that you can define. For example, scene query only draw line traces and not overlap and so on. We need to still continue iterating on this user interface to make it more UX friendly, but I just want to highlight that. If you are in the 5.4 version, the UI works, but at least it's documented, so I will show you at the end of this presentation a link to the documentation. Then the part of the last big part of the presentation mode before we go to the live demo, I want to touch on the playback controls or timeline controls. Before I made an analogy that the Visual Debugger interface is for physics kind of video player. For the Chaos Visual Debugger, it's more like a video editor in the sense that you have a main game frame timeline that represents every frame that was recorded during the recording session. But then we have multiple tracks that represent each physics solver instance that was running at any given frame. We also have playback control for it. So I want to touch on why we have multiple tracks and multiple controls. So there are a few reasons. I will focus on three. The main one is we support record multiple worlds at the same time. This is very handy, for example, if you are debugging a network multiplayer game in the editor. Let's say you set up your editor to do a play editor session with play as client where you have two clients. So what will happen under the hood is that you will have 3 world instances running at the same time, one for the server and one for each client. CVD is able to record the 3 worlds at the same time because each world will have its own physics simulation instance. So when you have multiple worlds, you will see in the Visual Debugger each track with multiple controls. But that explains why we have multiple tracks, but not why we have multiple dedicated playback controls. So one of the reasons for that is, I mentioned before, we support the new networking physics we are working on. The specific characteristic I will talk about is a rewind and resim. One of the latest modes we are shipping is the full resim simulation mode. This is a client side prediction based networking system where the client is always a little bit ahead because it's executing the input as they are executed. So it's predicting what the server will do eventually. But then if the server verifies what the client did and it didn't match, it will issue a correction. This is pretty much a standard client-side prediction. But for physics, what we do to apply the correction, we need to rewind the simulation state and then resimulate as many frames we need to get to the correct frame number we should be in. And the Visual Debugger supports this, allows you to visualize this. And what will cause the consequence of having this rewind and resim is if you are playing back from the game frame timeline, there will be a frame that instead of being 1 game frame equals 1 physics frame, 1 game frame might equal 5 physics frame because for those were resimulation. So if you are using in the Visual Debugger playing back using the main playback controls, that will represent what was visual in game. So you will see when the correction happens, a snap. Well, it's not actually a snap because we have interpolation, but I want to say the correction will be visible, but you don't see any step that happened in the middle. So you want to see how everything happens from the point of view that the solver that was resimulated, you can just play back from one of the affected solver timeline. You will know because it's not visible here. It was looping I think I failed to make this video loop, but there should be a blue badge here that tells you this solver is resimulated. So if you click play from there or scrub the frame from there, let's say the correction happens in frame 11. You play back from the main game frame timeline, you are on frame 10, go to 11, you will see the correction. You play back from the solver track, you are on frame 10, go to 11, you will see how everything was rewound back. You see the data was correct. And then you can advance for each frame that will be the resimulation. So you will see everything that happened in the middle. Otherwise, you would have missed, which is very handy if you are trying to debug an issue where the rewind and resume didn't correct the synchronization between server and client. We can happen for multiple things. A bug in Chaos could be more likely as well that it happened to us. It's a gameplay system that is modifying the physics properties of an object different in the server and client. So you will never recover for that, but you were able to see the difference in the state using the Visual Debugger. And one of the last things is also a little bit bigger, is async physics. Because rewind and resume has this situation where one game frame can be multiple physics frames, but there is a fixed offset, right, that you can calculate. But for async physics, it's an experimental feature that we use in Fortnite, and eventually, when it's ready, we will ship it. Async physics has the layer of complexity that one physics frame start not necessarily means that is the game frame start, or the end of a game frame is not necessarily the end of a physics frame. So you cannot map one-to-one just using offsets. So I want to show you how that is supposed to work. It's same as before. I think it could be a standalone useful piece of information, but also I hope it helps make sense why we show the way we do in the Visual Debugger. So to recap, this is the graph I showed before: sync physics, game thread at the top, physics thread at the bottom. The frame starts, push the data into the process, and then start the physics work, and then it needs to wait. Async physics remove that wait. So when you remove that wait, there are a few different scenarios that can happen now. So for this presentation, let's just assume that both are targeting physics thread and game thread are targeting have a delta time of 60 milliseconds to reach 60 FPS. In this screenshot or graph, it's trying to illustrate the scenario where both were able to achieve the work they needed to do within the 60 millisecond time frame. So nothing changed in practice. The wait is no longer there, but one frame equals one physics frame, because when the game thread attempt to finish the work, the physics thread already completed the work. So nothing changed here. The interesting scenario is this one, where let's assume same as before, game thread and physics thread are targeting 60 milliseconds. But in this case, the game thread is struggling. At the previous frame, we have a very bad hitch, and it took, let's say, 80 milliseconds instead of 16. It was a very bad hitch. But the physics thread didn't have any issue at all, was able to complete the work well within the 60 millisecond delta time target. So what happened here, in this new frame, the game thread, again, will push the data into a process to the machine learning manager, but then when it will starting the physics work, it will realize that since the last time it issued a physics task, only 80 milliseconds have passed, but the simulation only advanced 60 milliseconds, because in the normal circumstances, we will launch one physics work per game thread. But we are way behind now. So what the game thread will do now, it will try to catch up. And to do that, instead of issuing one single solver task, it will issue as many tasks needed to catch up with the time we have accumulated. So let's say in this case, we will launch 4 tasks instead of 1. So it does that. It issues 4 tasks. You can see the physics thread will start processing one by one, same as before, pulling data from the machine learning manager and pushing results back. But in this particular frame I'm trying to show, the game thread had actually a little bit of easier time. So it was still not great, but it was able to complete this frame a little bit sooner. So let's say what happened here, what I'm trying to show is when the game thread is trying to pull the data back for the Chaos machine learning manager, we still have one of the solver tasks in flight. It's not completed yet. Before, within physics, that should not be possible because we have a wait here, but the wait is not there anymore. What happened here is just that the Chaos machine learning manager will figure out, okay, yeah, there is a task in flight. They only have the latest available results from the previous task. So it will return that. The game thread will consume the work from the previous solver task was executed and move on to the next frame. Eventually, everything will line up again. But this presents a challenge for the Visual Debugger, because you want to have a main frame timeline show you what happened in game, and then we want to have multiple playback controls from each solver to show you what happened from the point of view of the physics solver, like we show in the rewind and resim. It means we can no longer map one frame to another using offsets. So what the Visual Debugger does is use timestamps. So each time you are scrubbing, going to frames in the main game frame timeline with a solver, internally we figure out what frame we should be showing for any other track using a timestamp, which is basically what the runtime system does. A Chaos Machine Manager also uses timestamp to figure out what result should return. The reason I'm mentioning this, aside from being a useful piece of information, is this means let's say you are debugging something that has async physics in the Visual Debugger and you are scrubbing frame by frame. You will notice that sometimes when you go, for example, for the main game frame timeline, the one, okay, I don't have the graph here, I actually have. At the top, basically you advance one frame, but you might see one of the other ones maybe jump 2 frames, 3 frames, kind of random, but it's not random, it's because what I just said in async physics. That was the last heavy graph part of the presentation. So now I have one last thing I want to talk on the playback controls is something you might notice. There is more, but I had to cut it out because I have 3 minutes to say this, otherwise I will be in trouble. The other thing I want to highlight here is you might see that each solver track has another timeline control on the side. So this is because the Visual Debugger is not only able to record the state of the simulation at the end of each physics frame, it's also able to record the simulation at different checkpoints within a frame or solver stages, that is what is called like that. So for example, you can make the Visual Debugger record also the state of simulation right after we do the narrow phase. So that is what I mentioned before, you can inspect the potential colliding particle pairs that were generated in the broad phase because we can record right at that point. But also you can record after the narrow phase where all the contact manifolds are already created, but we still didn't do any solving. And the way you do that, by default, when you are playing back, with ignoring that secondary timeline, we will just show the latest available stage that was recorded. Usually it's the end of the frame for each physics frame. But you can just pause, and then you can use those arrows to scroll back and forth in time to see the state on those stages. Lastly, one thing I want to mention as recording the state of simulation multiple type of frame is a lot of overhead. You don't need it. We disable it by default. I will show you in the live demo what it is, but there is a data channel dropdown that you can control, for example, enable those stages so it got recorded, eating the performance cost of doing so. Also, we have, for example, you can disable sharing constraint or the additional structure I showed you before. This is a way to, if you are investigating something that you know you don't need a specific piece of data, you can reduce the file sizes and the performance impact by just disabling the data channel. So, live demo time, and here is where I have been praying that everything works. So, I should have Lyra here. Perfect. So, if I want to show you, ideally, we should have 2 monitors. Ideally, it's best to work with 2 monitors, but you can only work with one. Use just snapping windows. But in fact, you don't need 2 monitors at all if you use the record to file. So you can inspect it later, but I want to use the fancier mode that looks a little bit cooler. I don't know, maybe it's not that useful for this case, which records live session. I want to see the visualization in the Visual Debugger as it happens in the game. So in this case, 2 monitors is the best, but you can use the snapping feature as I'm doing here if you want. So I have the game running. And you can start to see what's happening in real time. You can click the button Record Live Session. This is the data channel menus I just showed. Let me enable shines because I want to show some ragdolls that Lyra has. So click Record Live Session, and automatically the Visual Debugger will start visualizing what is happening in the scene. You can see the capsule from the characters running around. Let me see if I can find myself. Yeah, I think this is me, I guess. You can use the F8 key to lock the camera to any specific object, and then when you move the CVD camera will follow you, which is useful not just for live debugging, but also if you are trying to, you know a object will have an issue, but you know which frame it is, you can just select it, make the camera follow it, and click play. So I think we have enough data for what I wanted to show, so we can stop. Let's maximize the Visual Debugger. For what I want to show you now, let me find when I was eliminated and eventually I became a ragdoll. Okay, I just want a ragdoll, it seems that this was not me, but this also works. So the first thing I want to mention here is, I mentioned before, we see all the collision geometry. We have different ways to colorize it. By now, it's colorized by particle state. This is controlled the show menu. You can see the colors, here. Dynamic yellow, which will mean awake, and sleeping, red, kinematic blue, and static, and we have in grayish. If you train the preview version of Reim 5.5, create a reset default because it's an issue we'll fix for the full release, but otherwise you can ignore it. Also, you can colorize by shape type. For example, want to see at first glance if you have complex geometry that should not be there, you can switch to this mode, and you can see every that is a complex shape, in the case a triangle mesh color, it will be orange like this happening here. So let me go back to a state, and the thing I wanted to show is, you see everything is kinematic here because it's being controlled by the animation, but as soon as I get eliminated, we switch to ragdoll. You can see how the bodies are awake, we start simulating. Something we can see here, as we enable joints, we can also visualize the joints. We can mention each category has an enable draw. You can click it, and you can see each representation of the joint. In fact, each category has a section of subshapes. For example, let me see, joints. I can enable the stretch. I can enable, if you want to see each axis, or center of mass, connector, and let's say you want to see the state of that specific joint. In fact, this always is updated as it moves. You can just click on them. Let's say I click on this. It will get a little bit thicker. I don't know if it gets visually on the projector, but that's the physical selection. And then we have the details panel mentioned before. We have the state. We know this is not broken. We have the linear impulse, angular impulse is set to 0, and we have the settings, the stiffness, and all the settings used to create this particular joint constraint. Another thing we can do, also, let's say something later has, let's say you are debugging an issue with the sync queries I mentioned before. Something we can do if you want to debug the sync queries, you can go to the sync query menu. First, to reduce the visual noise, let's disable joints. You can go to the sync query flag menu. You can click enable draw, and right now I only enable line traces, so we can see every line trace that happens in this frame. And obviously this gets updated each time you move. If you want to see details about a specific line trace, you can just click on it. And you will get, again, I mentioned before, that all the inputs that were made to create this query. This is a rate cut in test mode. We have the start and position. We have the queries, like for example, this is not tracing against complex geometry. This particular query is ignoring a specific actor. We have the name here. We have the collision trace response matrix. It seems it's switching the default, everything to block. Nothing changed here. And it seems this query hit something. And we have the hit type. We have, for example, data the hit about the distance, for example. And if you want to see a specific hit, each hit is represented like a circle in the orientation of the plane that the hit was detected. For example, you can click on them, and we'll get a yellow box giving you some feedback of the selection. I mentioned before, I don't have too much time to find a good example of this, but we record each shape that was evaluated as part of this query. For example, in this one, it seems 11 shapes, 11 collision geometry was evaluated as part of the line trace to detect the hit. So you can just, right now we're in 0, you can click select particle, and it will select each particle that was visited. You can go to the next, and you can select particle, and we'll select it. And you can see every shape that was evaluated. This was a very long line trace, so basically it seems it evaluated pretty much the entire level. The last thing about the sync queries I want to touch on is let's say you don't know where the query you are interested in is. So something you can do, you can go to this is a 5.5 feature, it's not in 5.4, sadly. But you can go to the async query browser. It's basically a detailed async outliner for async queries. You can see most of the queries are hidden because I only show inline traces. We have the same menu as the show menu. You can enable everything if you want. Then we are seeing the sweeps and everything. And you can just double click on any query by name. And we get teleported to it. And one last thing I want to touch about this, I'm already running out of time, is let's say, for example, you have an algorithm that doing multiplexing queries one after the other within a single frame, and that algorithm branches depending on the result of the previous query. You have everything enabled by default, even with a single frame, can be a little bit of visual noise. For example, we see all the sweeps from the character movement component here. Something we can do, you can switch to a mode that is recording order, so that the Visual Debugger will only visualize the queries in order and then enable this timeline in the bottom where you can see, for example, this particular query was done first, and then, for example, this one. Yeah, this is the same actor, these two. So this first, we have this sweep for the movement component. It seems it's one horizontal sweep. Then we did another sweep with the same actor. And then we did a vertical sweep to compute the floor distance. So we can see it in order. We don't need to see it everything at the same time. Yeah. So I think that will be for async queries. The other thing I want to show you, I will take the opportunity to do another risky thing. I do a different kind of demo. I should have 1 second. I want to show you how to do a recording from a package client. So I have a modified Laravel. So let me see if I can get that going. This is a development build because I forgot to mention, CVD is compiled out in shipping builds for performance reasons. So it's only available on test and development builds. Test build will have the issue of any names are compiled out, so everything in the single liner will have no names. So ideally, if you can, you should use it in development build. So let's play it later. Let's start a game. Let's start, with control. The same as we were before. I broke something intentionally in the game, but I'm running out of time to make me like a dumb person. I don't know what I broke. I know what I broke. You can go through the wall, and that should not be possible. Okay, I didn't want to go there. So you want to see what is happening. You don't have the specific version of the editor with this level. You can just start a CVD recording. For 5.4 or 5.5, in a package build, you can only do it with a console command. In the future, we want to be able to do it from the editor. But for now, you can use I will say it, but it will be in the documentation, so don't worry, is pet.chaos.startVD recording. And when you start recording, you will see a message at the top of the screen telling you that the recording is active. And when you are doing that, you can just try to reproduce the issue. I got eliminated in the most inconvenient time. Okay, I just want to go through this. And then you can stop the recording, pet.chaos.stopVD recording. And now that recording should be in the profiling folder of this particular package build. So to open that, you can go to Tools, Debug, Chaos Visual Debugger. You can now use the Open to File button. And I don't need to go to a specific profiling folder from the editor because this is a package build. So I hope I'm not showing something I should not show here. Let's just in case move this. Okay, this is safe. Laravel, package build, Windows. Okay, the profiling folder is in the save folder of the editor of the package build we are going to. So save, profiling. We need the one from the last one, date modified date, October 3rd, 10:39 a.m. This one, you can open it. you get the same as before. It have all the inquiries enabled because it's what we were seeing before. We don't care about that. Let me disable that. So this was one of the things we were going through. Let me advance. Yeah, I see myself. I think this is myself, or was close to the end. Yeah, I'm going through the wall there. So a few things we can get from this is visually we know the collision is there because we see the shape there. We know it has physic enabled because something I didn't mention before is anything that, for example, is query only is translucent. That is what the capsules and the rigid bodies of the ragdoll are translucent because that is query only. We know it's at least has some set of collision enable settings set because we can see it, the world. But if we want to see the collision presets, and I mentioned before, when you click on something, or I didn't mention before, you will see the particle state of the particle you are selecting. In this case, it's a static particle. That is why you only see the transform. But let's say I select the capsule that is a dynamic kinematic particle. We can see the acceleration is a kinematic object, basically has gravity enabled, all the flag, pretty much all the data. But you hold the left shift key, you enter it another secondary visualization mode where you see the data in the data panel about that specific collision geometry. For example, if I click on this, holding the left shift key, I see all the shape data I mentioned before associated to the collision geometry. So here we can see this is a tree mesh. This is set to use complex and simple geometry. Is collision enabled query and physics. So this should be working. So we can continue seeing, okay, what are the collision profile settings that we are using? And we can see everything is set to block except to pawn a physics body. As I'm running out of time, I can tell you this is the thing I broke. This should be in block. So yeah, way you can confirm it. I can just click on another wall here, this one here, and can see that pawn and physics body is set to block. So you can use this. You are doing a sync query, and or another reason that you didn't get a collision that you were expecting. Didn't work, you can verify that the asset was set up correctly using this. You can just inspect the collision matrix, collision response matrix for each geometry. Something I didn't show before, I was supposed to show before, but I forgot that I had this ragdoll here very conveniently. I mentioned we can see the collision data. We also record collision data. We can enable draw here, and we should be seeing, a contact points, for example, collision point between the ragdoll, in case the foot and the floor, and those are visualized as circles representing, same as in query, the orientation of where the contact normally is pointing to. You can select them, and you can see pretty much entire state for that constraint contact. You can see the net push-out force that was calculated. You can see more information about the contact point. Basically, it's a contact between a vertex plane. We can see the the physical material used that was calculated for that constraint based on the physical material, so each shape. We can see this is a collision type, is a box against a tree mesh because the foot is a box and the floor is a triangle mesh. Collision margins, all the points of that constraint, because right now we are seeing at the top the data for that specific contact points, but this particular particle pair are having multiple contact points. You can see the entire contact manifold here. If you don't know, the seat is more noisy, you don't know which particle it is, you have to button here to select one of the particles. You can confirm that is the foot, and the other one, we can confirm that is the floor. So you can inspect pretty much the entire collision settings. And yeah, you have more things to enable, like for example, you can visualize the vectors of the contact. And one last thing I will rush through it. I mentioned all the data I mentioned about acceleration, velocity, we can see about the particle. We also can say, what is this? In particle data, we can just enable draw, and it will draw each thing you have selected. Like for example, velocity is a vector you can see visually. You can do it per particle, you don't need to do it everything at once, but it's something you want to try to see an issue visually and not just looking at the details panel. what I'm trying to get is most of the data that is available in a details panel has some kind of visualization also in viewport that you can enable. And also, I think this shows why having everything enabled at the same time is just visual noise. That's why I disable it. And I think the last part of the last demo, I want to do is I mentioned CVD project independent. So I didn't need to close it, but just in case. I have a complex file recorded from city sample, and this is Lyra project, so I don't have anything about city sample. So let me open that. I think it should be Lyra build. Yeah, city sample and reference demo. This is a very large file. It's a 2.5 gigabyte file. It got the entire city sample work that was recorded. And something we see that didn't happen before. You will see a progress bar. You see everything popping up. That is intended. So I load that. There are 500 frames. It's still loading, but while it's still loading, you can just teleport and start debugging right away. We don't need to wait for the data to be fully loaded. Obviously, as it's loaded, it will struggle a bit. Let me disable that. Particle data. Perfect. And let me make CVD follow that. I think I also have a collision flags enabled. Yeah. So yeah. If you follow that and you work in this advance where a vehicle is driving, you can see the geometry was not ready because as being project independent, CVD needs to generate all the static meshes on the fly based on the geometry work. We just record the raw geometry data. We don't record a mesh or anything. So if you, for example, get to a big collision or anything, let's jump in to trigger that. And CVD needs to generate a lot of geometry. It will use a pop-out in the bottom that it will generate the geometry. I will see things popping up, but should be able to still play back. You will not be blocked too. In this case, it's a good case to mention multiple solver instances. I didn't mention before. CVD supports, for now, only the rigid solver and rigid urban solver, rigid body animation solver. So we can see both playback at the same time here. So it's not just for client and server physics. We have plans in the future to support the cloud solver and other body solvers, but for now it's just the rigid solver. Yeah, I think that is pretty much it for the light demo section. So I simply have 10 minutes to go to the last slide. I want to talk about the future plan for the Visual Debugger. So now that we see how CVD work or what you can expect, I want to talk next. What will be coming next? First, I want to mention performance improvement. I mentioned before, for example, that city sample demo, if you tried in 5.4, it will work, but you will see the progress bar blocking a few times. So it was a little bit rough. For 5.5, it's way better, but I still have a lot of things I can do to even faster and use rare resources. But yeah, that is an ongoing work. The other thing I want to mention is more way to filter data. Right now, we record a vast amount of data, but we don't have a lot of ways in UI to allow you to fine-tune what you want to see. For example, we have the show menu with multiple flags, but let's say, for example, you want to see a specific collision particle that has a specific particle that has a complex collision that responds to a specific collision channel set to overlap instead of block. We have the data in CVD to be able to figure out that, but we don't have a user interface to allow you to tell CVD, only show me this in this way. So what I wanted to do, we'll continue adding options like that, like the show menu and the user interface, but the end goal for me will be to have some kind of scripted system. This is pretty much CVD, the idea that you have an API exposed to blueprints, like an editor till widget or something like that, where you can have access to an API to get all the process data in CVD and do that kind of query I mentioned before. And when you get a set of particles or rigid bodies that match that criteria, you can tell them another set of API in CVD, okay, colorize these particles in these colors, or select that, or just print a list of names. So allow you just to create your own set of visualization rules for the Visual Debugger with the data we have there. And the other good feature I want to do is CVD extensions. Right now, everything you see from the engine data, but we want to allow you a way to buy a new plugin or module from the game side of things, define your own serialization types, your own data types, and so you can record game code data see it in the Visual Debugger, and not just define how to record it, but also how to visualize it. We will provide some pre-built ways to do it, but you can write your own. I basically expose all the APIs the CVD use internally to create, for example, how we visualize the inquiries. And then one of the last points I want to mention is simulation. Something we want to do for the future is, let's say you are at any frame of the simulation in the Visual Debugger, have a button to say resimulate, and we resimulate with the local instance we have built in the Visual Debugger from Chaos, resimulates an X number of frames. So you can test a code change you made in Chaos, for example, to see what is the result without having to go to the game. Or more interestingly, I think, useful thing could be, let's say, right now the data in the Visual Debugger is read-only details panel. You can try, let's say, we make something editable, like allow you to change the physical material settings in the Visual Debugger, and then rerun the simulation. How I envision it, this is pretty much DVD. It will be just appear as another solver track that you can play back side by side, so you can just A/B test the difference, and that will allow you to iterate, fine-tune physics settings in place very fast. The same thing for async queries. I mentioned maybe async query failed because you had the wrong collision preset. And with simulation, you should be able to rerun the query, changing the collision preset without having to do it in game. And then eventually, yeah, you will find game. But that is the plan long term. Much more. I didn't have time to put in here. Just to finish, there is an entire user guide for a lot of features I didn't went to in the Epic Developer community. Here is the link to it. This is the 5.4 version. There are a lot of things that are not available. They are in 5.5 that are not in the guide. The 5.5 version will be available with the full release of real 5.5. But this guide has enough data to get you started. You will notice the UI is a little bit different, a little bit worse. I hope. I hope the new one is not worse. But other than that, you should have pretty much what you need. So thank you very much for the time. Yeah.